Okay, so this is a video on orthogonal matrices. The definition of an orthogonal matrix is that P is n by n, such that P inverse is equal to P transpose. Then we say that we have an orthogonal matrix. Now this seems kind of strange to relate this to orthogonality, but we'll get the connection here. We immediately get a theorem that says that P, which is an n by n matrix, is orthogonal if and only if its columns form an orthonormal set. Alright, so P is orthogonal if and only if the columns of the matrix form an orthonormal set. Now what I'm going to do here is I'm going to prove the going from the orthonormal set to orthogonal. We're going to leave the other part of this for your, if you want to try to prove it, but we're going to just accept that in the course here, so I'm going to prove it going this way. So here's the proof of this way. We're going to let P be P1 column P2 out to column Pn, such that the set containing P1, P2 out to Pn is orthonormal, right? So that's the goal. Okay, so what we do here is now we want to take P transpose P, right? If I do that, then I'm taking P1, P2 out to Pn times P1, P2 out to Pn, and if I look at that, that's going to be row versus column. Row times column gets me P1 dot P1, and then this one will be P1 dot P2, P2 dot P2 out to P1 dot Pn, right? And then this gives me P2 dot P1, P2 dot P2 out to P2 dot Pn, and then I should get Pn dot P1, Pn dot P2 out to Pn dot Pn, right? So this is like that. An orthonormal, when it's something dotted with itself, I get a 1, otherwise I get a 0. And really quickly here, I'm going to discover that I get the n by n identity. So this implies that P transpose does the same thing as P inverse, which is what I want to prove, because this means that P is an orthogonal matrix. Alright, so we've proven it for the converse. We've not proven the direct statement, but it shouldn't be too incredibly far of a jump to see how the direct statement might be proved here. Alright, so let's get another theorem that might be relevant. Okay, so in this theorem, we're going to go back to, whoops, we're going to go back to A being n by n symmetric, and we're going to say that lambda 1 not equal to lambda 2 are eigenvalues of A that correspond to x1, x2. And then our argument here is then these eigenvectors, x1 and x2, are orthogonal. Alright, so we can prove this fairly straightforward. Alright, so we're going to let a times x1 be lambda 1 times x1, and b times x2, sorry, a times x2 equal to lambda 2 times x2. And we're also going to note that lambda 1 does not equal lambda 2. Right? Okay. So we start with lambda 1 times x1 dot x2. Okay, and a little bit of work here gives me lambda 1 times x1 dot x2. Right, so that's fine. This then is the same as a times x1 dot x2. Okay, but the dot product just means that I take this vector a times x1 and I transpose that and I dot that with x2. Okay, now you can convince yourself of this. Take a minute and try to figure out why that works. So that's not actually a dot there. I just take that back. That's a times x1 transpose just times x2. Okay, so work that one out. See why that works, why that is the dot product. Okay, so if I take the transpose of a product, that is going to be x1 transpose a transpose x2. That's by property, right? So, well, since this is a symmetric matrix, I get x1 transpose times ax2. Okay, that there is a dot product, right? Oh, we can just take this back to lambdas here. So this is going to be x1 transpose times lambda 2 times x2, right? Okay, so this is going to give me x1 dot lambda 2 times x2, right? So now we can bring that lambda 2 out in front. Lambda 2 times x, this should be x1. No, sorry, that's lambda 2, that's right. Times x1 dot x2. Right? So this is where I need to be. The implication here is that this and this are equal. So, bring it all to the same side, right? And I'm going to get lambda 1 minus lambda 2 times x1 dot x2 is equal to 0. This is all scalars, right? So since this can't be 0, that means that x1 dot x2 has to be 0, which gives me orthogonality. x1 has to be orthogonal to x2. So there we go. We've proven that. Alright, so we're going to take this one small step further. We're going to get what's called here orthogonally diagonalizable matrices. What are those? Okay, so A is going to be an n by n matrix such that there exists P, which is orthogonal, and D, which is diagonal, such that D is equal to P inverse A P. If I have this, then I say that A is orthogonally orthogonally diagonalizable. So it's a big mouthful to say, but it's basically saying that A can be made into a diagonal matrix using the inverse and itself of an orthogonal matrix. Great. Okay, so we're going to get into this thing that we are going to call the fundamental theorem of symmetric matrices. So, fundamental theorem of symmetric matrices. Woohoo. Alright, so what does this thing say? It says that if A is n by n and A is orthogonally diagonalizable, then and has real eigenvalues. So it's these things if and only if A is symmetric. Wow, that seems pretty wild. So if I have a symmetric matrix, it is orthogonally diagonalizable with real eigenvalues. And if I have something that's orthogonally diagonalizable with real eigenvalues, then I know I have a symmetric matrix. Okay, so we're actually going to prove this. So we're going to assume A is orthogonally diagonalizable. Okay, so this implies that there is some diagonal matrix equal to P inverse A P, right? Where P is orthogonal. Alright, so if I rewrite this, I'm going to get that A is equal to P D P inverse, right? Which also means that this is equal to P D P transpose because P is orthogonal. So this means that A transpose has to equal P D P transpose transpose, right? Which is just P D P transpose, because a diagonal matrix transposed is itself, right? So this is just going to give me P D P transpose, right? Which is the same as P D P inverse, which is the same as A, which means that A is symmetric. So I've proven this. Okay, so what about the other direction? Okay, so let's go to the left here, right? Alright, so we're going to assume that A is symmetric, right? If A is symmetric, then we're going to let lambda be an eigenvalue of A with multiplicity K. Okay. So this, because it's symmetric, implies that lambda has K linearly independent eigenvectors associated with it. Okay. Now, note, you can take this set of eigenvectors with Graham-Schmidt and make an orthonormal basis for the eigenspace of lambda, or, well, of A with respect to lambda, right? Now, I can repeat this for all of these distinct eigenvalues of A. So once I do that, I now have a full set of linearly independent eigenvectors that are orthonormal. Okay? So, well, think about what that means. That P, if I make P the set of those eigenvectors, right? So let's call it x1, x2, out to xn, and these are the orthonormal eigenvectors that I get as a result of Graham-Schmidt. Then, if I do this, then P is orthogonal. by definition. So that then proves the right arrow. All right, so like, who cares? Okay, so if I put EIG-A into MATLAB and A is symmetric, then I get a P that is orthogonal. Now, why does this matter? Because if I get something that is orthogonal, then P inverse is equal to P transpose. Now, this can really save me on calculations. Inverses are exceptionally expensive to calculate. Okay? Transposes are cheap because you just move stuff around and you change rows with columns. So if I can replace inverting with transposing, then I get a huge jump in my attempt to make cheaper calculations. So this is something that's a little bit of a deep cut in linear algebra here, involving eigenvectors and eigenvalues, but it's a trick that if you can get it to work using a symmetric matrix, you can get some really cheap calculations in places where you might need them. All right, so there you go.